let me begin by asking, does anybody have any review questions that they want to talk about? I'm totally happy to do this if anyone wants to, or if not, I won't. That's fine. Okay, I don't see anybody speaking up. Oh, Andrew, yes, sure.
Yeah, I have one question. So in the practice test, when there was a question asking about the oscillation period, for that, we're going to take whatever in the cosine, obviously aside from t, and set that equal to like 2 pi over t. And are we like capital T for period?
Mm-hmm.
Is that what we're solving for?
That's right. That's right. And so what you're saying is that if you have a probability density, for example, some p of xt, which is something plus something times cosine of delta E over h bar times t, something like that, for example, right? Okay, and you want to know what is the period, right? So you would take what's inside the cosine, right? The period of the cosine is 2 pi, right? And so when the argument of the cosine increases by 2 pi, that's a period. And so to find the period, you would set what's inside the cosine, delta E t over h bar equals 2 pi, and then say, oh, well, that must be t is 2 pi h bar over delta E. Okay, and so that's the period. Right. That's what you were asking, right? Yes. Okay. Good. And if it's something, if you get a probability density that doesn't depend on time, well, then it's not periodic, right? And so it doesn't really make sense to ask the question of what's the period then. And if somebody does ask you the question, your response might be, well, it's a constant with respect to time. Good, very nice. Anything else? No, and I don't see anything in the chat, though I'm not sure I even see the chat. Oh, here's the chat. Oh, okay, but there's nothing there. Sorry, it was when I do the iPad sharing, the chat kind of gets hidden. Okay, but maybe I can catch on to how to show it. All right. I don't see anything there either. Okay, well then, let's talk about something new. Okay, so in the class on Tuesday, I told you about the Dirac notation. All right, so the notation with bras and kets and operators. What I want to show you today is kind of an extension of that, which shows how this notation leads to a whole new approach to quantum mechanics. I'll call it the matrix approach to quantum mechanics, which can be compared with the wave function approach that we've been doing all semester. Okay, so let me show you how that works. All right, so let's think about what an operator does in terms of this Dirac notation. Okay, so here, what we discussed on Tuesday is that we can have an operator that acts on a ket and it produces another ket, which is the Dirac way of saying that if an operator acts on a wave function, it produces another wave function. Okay, so the wave function way of saying that is the operator Q acting on some wave function alpha of x produces a function beta of x. Right? So it acts on one function, produces another function. Okay. So the direct notation way of saying the same thing is that the ket beta is Q acting on the ket alpha. Right? So this alpha of x, is written as a ket like that. The beta of x is written as a ket like that. So Q acting on the alpha ket produces the beta ket. Okay, now suppose we want to express these kets in terms of a basis. So a basis, as we talked about, is a set of kets that can allow you to expand any arbitrary ket in the Hilbert space. Right? So the same way that for a vector in 2 dimensions, you can express it as something times x hat plus something times y hat, right? Or a vector in 3 dimensions, something times x hat plus something times y hat plus something times z hat. Okay, and so here that works for kets, right? So we have a basis, a set of kets like 1, 2, 3, ... Now there might be infinitely many kets in this basis, but that's okay. We can generalize the concept of a vector space to be infinite dimensional. All right, so that means any ket can be expressed in terms of a sum of some coefficient times 1, plus some coefficient times 2, plus some coefficient times 3. Okay. That works for any ket. So it should work for alpha. It should also work for beta, right? Each of those things can be expressed as in terms of that basis. Okay, so let's do it for alpha. Okay, so alpha is going to be a sum over n of a coefficient an times the ket n. It also works for beta, right? And so the ket beta should be a sum over n of some other coefficient, bn times the ket n. Okay, so these things are constant coefficients. I don't even need to say constant. I'll just say these things are coefficients, okay? And so, yeah, these things are coefficients. All right, so this is now, what it means to work in a basis, right? So the same way that any vector in 3D, this vector has an x component, a y component, and a z component. Right? So the ket alpha has a set of components, which are all these a's. The ket beta has a set of components, which are all these b's. Okay. Now, I wrote on the last slide that beta is equal to the operator Q acting on alpha. Okay, so if I want to put now, okay, so now suppose I want to express alpha and beta on both sides of this equation in terms of these coefficients and the basis. Okay? So for beta, I put in the sum of Bn times the state n. So that equals Q acting on the sum of An times the state n. But now, because Q is a linear operator, all the operators in quantum are linear operators, it can go inside the sum, and it can go inside the coefficients. We can pull the coefficients out in front of Q. So this is the sum over n of An times Q acting on the state n. Okay, now we might ask, what is the relationship between these coefficients, the b's, and these coefficients, the a's? If we want to figure that out, let's act on both sides with a bra. In particular, let's do the bra M like that. Okay, so that means we're going to say the bra M hits that, it hits that, and it hits that. Now let's simplify a little bit. Okay, on this side, the bra can go inside the sum. It can go inside the multiplication by b, right? Because what the bra does is linear, like what the operator does. Okay, so this gives us that the sum over n of Bn inner product of M with N, like that, that is equal to, and now if I work on this side, that is the sum over N, An still factors out. We have the bra M acting on Q, acting on N. Now, we can simplify a little more because, this inner product right there, that is the Kronecker delta of Mn, right? Because our basis is orthonormal. So if we have a basis of energy eigenstates, or position eigenstates, or momentum eigenstates, or any old eigenstates. Right? It's a set of vectors which are orthogonal to each other and which are normalized. So this inner product is the delta Mn. Okay. And now we can simplify the sum on the left side of this equation, because it's a sum of an infinite set of terms, but only one of the terms is non-zero, and that's the term where n equals m. And so this simplifies to just bm. Okay, so now this is telling us what are the b coefficients in terms of the a coefficients. Okay? And I can rewrite this equation to make it something that maybe we can recognize. Okay, so let's rewrite that as bm is a sum over n of this combination, the bra m acting on the operator q, acting on the ket n times an. Right, so I'm just putting the an on the right side there because this is a number and this is a number, and so multiplication of those numbers is commutative. Now, the point is that this is very similar to something that you might recognize from linear algebra classes. Okay? Here we have this object, which we could write more compactly as Q sub mn. Okay, and this is what we call a matrix element of the operator Q. Okay, so this is something which characterizes what Q does in terms of the basis. Okay, that Q acts on one basis vector, right? So the n vector goes into Q, and it makes some component along the m basis vector, and that is the matrix element. Okay? And then this whole construction looks like matrix multiplication. So this might or might not be clear to you. Let me try to write it out in another way that maybe is more recognizable. Okay, so it means if we have a set of the B's, okay, we have B1, B2, B3, dot, 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 right? So an infinite set of the B coefficients. Okay. That is something that I could say that's a column vector of the B coefficients. That is related to a column vector of the A coefficients. Okay, so these are column vectors that are infinitely long, but that's okay. We're going to still work with them. But still, it's just like the column vectors that you would have seen in a linear algebra class. Okay, and then these things are related by multiplication with a matrix. Okay, so there's a matrix of Q11, Q12, Q13, then Q21, Q22, Q23, Q31, Q32, Q33, right? And this goes on forever, infinitely long in two dimensions, okay? So this is now a matrix representing the Q operator. Okay, and so the way that you combine the matrix for Q with the column vector for the A's is by going across this row and down this column. Okay, so it is Q11 times A1 plus Q12 times A2 plus Q13 times A3, continuing this way and this way, okay? And that makes B1. Okay. Likewise, for the next row, the second row, B2 is Q21 times A1 plus Q22 times A2 plus Q23 times A3, etc., etc. Okay. For the third row, it's Q31 times A1 plus Q32 times A2 plus Q33 times A3, etc., etc. Okay, so that rule for matrix multiplication, right, which you learned, in some math class in the past, that's the same thing that's written in this equation right there. That's saying that M is the row number and N is, no, oh yeah, M is the row number. Okay, and then for N, that's changing the column for Q and the row for A. Okay, and so if you want row number M, you look at row number M here, and you have a sum over all the columns of Q and the rows of A. Okay, that's the rule for matrix multiplication, and so this is a form of matrix multiplication, right? And so it's telling you that what the math teacher taught you back then, it may have sounded totally arbitrary back then. Say, what, you want me to multiply matrices like this? Why, right? And so here you can see a reason why, right? That the matrix multiplication corresponds to this operation of an operator. Okay, so the moral of this story, is that we work in terms of a basis the ket is represented by a column vector. Okay, and the things that go in the column vector are, we could say, the ket alpha is represented by this column, A1, A2, A3, etc. Right? And the things that go there are these inner product of 1 with alpha, bra 1 with alpha, bra 2 with alpha, bra 3 with alpha, because I showed you on Tuesday, right? These are what the coefficients are, right? If you're trying to calculate each of these coefficients, you take the bra, if your coefficient 1 is bra 1 inner product with alpha. Coefficient 2 is bra 2 inner product with alpha, etc. Okay? So this is a way of writing the ket not as some abstract function, but as a column of numbers. And so we would not necessarily be writing some psi of x. Any psi of x then can be summarized as a column of numbers like this. Okay? And likewise, an operator is represented by a matrix. Okay, so the operator Q corresponds to the matrix. Maybe I won't say equal, I'll just say arrow, right? This is alpha is an arrow, is this thing. So Q is a matrix which is 1 bra 1 acting on Q acting on ket 1. That's what goes in the 1, 1 place. And in the 1, 2 place, we have bra 1 acting on Q, acting on ket 2. Okay? And then here we have bra 2 acting on Q, acting on ket 1. And here is 2 acting on Q, acting on 2. Continuing on, both in rows and in columns. So, instead of thinking of the operator as, something like a derivative that acts on a function and produces a function, right? That's still true, but a different way of thinking about the operator is as a matrix, as this table of numbers, right? And that summarizes what the operator does. Right? And then, following the same kind of argument, we could say that a bra is represented by a row vector. So the bra alpha, like that, it corresponds to a row vector, which is the set of complex conjugate coefficients, A1 star, A2 star, A3 star, ... And these coefficients are the bra alpha acting on the ket 1, and then the bra alpha acting on the ket 2, the bra alpha acting on the ket 3, etc. And then once you have these things, you can combine using the rules of matrix multiplication. And so in particular, if you have a bra acting on a ket, okay, that makes a row vector acting on a column vector, And you know, when you combine these things, you multiply first times first, plus second times second, plus third times third, etc. And this produces a scalar, which you already knew, that a bra acting on a ket makes a scalar, right? And so then similarly for operators, right? The operator acting on a ket is a matrix times a column vector. Right? And this is a ket, right? Because that's how you multiply a matrix times a column vector. Or if you have a bra operator, that would be a row vector and then a matrix. That makes a row vector, right? So that is what you would multiply out, you know, for the first element, this times this, plus this times this, plus this times this, and that goes in the first place. And then second place, third place, right? So that's a row vector. So that is a bra. And you could also do the, you know, the opposite of this thing, right? So here the scalar is the inner product. If I want to do the outer product, I would say, let's do a ket bra. So that is a ket, a column vector, times the bra, a row vector. So that makes a matrix, right? If you are multiplying a column vector times a row vector, following the rules of matrix multiplication, then first you multiply this times this, and that goes here, right? And then you multiply first times second, and that goes there, right? And so there's no adding. It's first times third goes there, right? So this is a matrix, and we know that a matrix is an operator. So this thing is operator, which is the outer product. The bra times the ket. Okay, so this turns into a whole way of thinking about quantum mechanics, which doesn't have wave functions in it, and it doesn't have derivatives in it or differential equations. Instead, it's an approach to quantum mechanics which is based on these vectors and matrices. Historically, I believe that this matrix approach is what Heisenberg first came up with for quantum mechanics. And then Schrödinger came up with the wave function approach. And at first, people thought these were two different theories, and they had to figure out which one was right. And then it was only several years later that people understood that these are actually equivalent to each other. These are two different ways of thinking about the same thing. Right? And so that's what we're getting to here, right? Is how to express everything in terms of matrices and vectors, just sets of numbers, and it all works, right? Just as long as we keep in mind the rules of matrix multiplication, and as long as we keep in mind that we're working in terms of some basis, right? That all the numbers are numbers expressed in terms of the basis, which is the basis that I started with way back here. So that could be the sets of eigenstates of anything, energy or momentum or position, right? We just get to take our choice like that. Okay, so is this kind of clear to you guys to begin with? All right, so I mean, I'm trying to present an alternative point of view, right? And so it's a point of view that covers the things that we've done earlier in the semester, but using matrices instead of functions, right? And so in some sense, that's the payoff from all the Hilbert space stuff that I've spent a few weeks on now, is to be able to make the switch from functions to vectors. Okay, so what I want to do now is to try to tell you, or to show you an example of how to do parallel calculations, right? So how to do a calculation all using the wave function approach, which is kind of familiar to you, versus how to do it with the matrix approach, okay? And to show you what are the analogies between these two things, right? How these are consistent with each other. Okay, and so I'm going to start making a giant table here. Let me see if I can do this. Okay, so I'm going to make a giant table where I compare the matrix approach with the wave function approach. Okay, so let me try to express this concept in the form of a children's story. Okay, so I want to say, for the matrix approach, right? Once upon a time, there was a poor little electron that could only live in two different possible positions. Okay, so I'll call those things position 1 and position 2. Okay, or better yet, I'll say ket number 1 corresponds to the electron at position 1. And ket number 2 corresponds to the electron at position 2. So this poor little electron can only be in those two possible places, okay? And it could also be in a combination of those two states, right? So we could say the state of the electron is something times state 1 plus something times state 2. Right? So these are two coefficients that go in here. And so let's call those coefficients psi 1 of t and psi 2 of t. So in this point of view, right, that's what it takes to describe this poor little electron, right? The two functions, psi 1 of t and psi 2 of t. Okay. And by comparison with that, there was once a rich electron who could go anywhere he wanted on the x-axis. Okay, so this guy has a wave function, which looks like psi of x and t. like that. Okay, so what I want to do is to point out an analogy between the theory for this two-state guy who has these two functions of time, not functions of x, functions of time, okay, versus this one who has a function of position and time, okay? So that means, there's a function of time at, x equals 1 centimeter, and a function of time at x equals 1.1 centimeters, and a function of time at x equals 1.2 centimeters, right? And at any particular value of x. Okay, so now what? Okay. We could write these two sides over on this right side as a column vector. We could write it as psi 1 of t, psi 2 of t, like that. Okay, and so this column would be a nice way to describe the state of the poor electron over there. Now, what if we measure position? If we measure the position, we could get two possible numbers, right? We could see that with a probability psi 1 of t magnitude squared, that is the probability that the electron is at position 1. And psi 2 of t magnitude squared is the probability that the electron is at position 2. Okay. By comparison, if we measure position over for this electron, then, well, we you know about that, right? You know that this psi of x and t squared dx is the probability that the electron is between x and x plus dx. So, with probabilities, we have to do things a little bit differently when we have a continuous x versus two possible states. Okay, and so when there are two possible states, we have two probabilities, right? These two probabilities. And when there's a continuous set of positions, then it's a probability density. Right? And the probability density gets multiplied by that tolerance dx to give you the probability. But in either case, there has to be a constraint of normalization, right? That in any probability problem, the total probability has to add up to 1. Right? So there must be a normalization that this psi 1 of t magnitude squared plus psi 2 of t magnitude squared equals 1. Right? The total probability for the electron to be somewhere has to be 1. And that's just like in this wave function approach. The normalization is that the integral from minus infinity to infinity of psi of x and t magnitude squared dx equals 1. Okay, that those are analogous statements for the continuous versus discrete cases. Okay, we good so far? All right. Okay, now, how about for the position operator? Okay, so with the wave function approach, we know that there's a position operator x hat, okay? And so what that operator does to a function is just multiply it by the x, the position. So suppose we wanted something like that that works in the matrix approach, okay? So we want to make an operator such that x hat acting on the state 1 equals 1 times 1. And x hat acting on the state 2 equals 2 times that state 2. Okay, so this would be sort of analogous to what the position operator does here, that x hat acting on f of x equals x f of x. Okay, it just multiplies by the position. Okay, we can do that, right? So we can make a matrix which does this thing over here. Okay? The way to do that as a matrix is to say, well, I can write it in bracket notation, or I can write it in matrix notation. Okay, in bracket notation, that would be x hat is 1 times the outer product, 1, 1. Okay, so this is a projection operator, like we talked about at the end of the last class. And then plus 2 times this projection operator over there. Okay, so this construction, it does the job, right? Because if we let this thing act on the ket 1, okay? So if we have this, whoops, let me write that out. If we have this combination, so funny looking notation, but okay. And this acts on the state 1, on the ket 1. This produces 1 times this inner product plus 2, ket 2 times this inner product. This inner product is 1. This inner product is 0. So this is 1 times the state 1. And likewise, if we repeat all this with the state 2, if we repeat all this with the state 2, we would get 2 times the state 2. Okay, so this is one way of writing the operator x hat. Okay. For another way of writing the operator x hat, we could write it as a matrix. Okay, so to write it as a matrix, we could say let's make a matrix of x, 1, 1, x, 1, 2, x, 2, 1, x, 2, 2. Okay. That is a matrix of 1, x, 1, like that. And then 1, x, 2, 2x, 1, 2x, 2. Okay, so, what are these things, right? Well, 1x, 1, that is 1 acting on, well, we know what x hat acting on 1 is. X hat acting on 1 is 1 times 1. All right, so this is just the inner product of 1 with 1, which is 1. Okay. 1, x, 2, all right, this is the bra 1, and then x hat acting on 2 is 2 times ket 2. So this is 2 times the inner product of state 1 with state 2, which is 0. Similarly, 2 acting on x, acting on 1, that is 2 acting on 1 times ket 1, which is the inner product of 2 with 1, which is 0. And 2 acting on x, acting on 2, that is 2 acting on 2 times state 2, which is 2 times the inner product of state 2 with itself, which is 2. Okay, so as a matrix, the position operator is the matrix 1, 0, 0, 2. Okay, so in this approach, everything we need to know about the position operator is in this table of numbers. Okay, and then we could say the states, the states 1 and 2 are position eigenstates. Okay, so that means that the position operator acting on 1 is 1 times state 1. Okay, so this is an eigenstate, and the corresponding eigenvalue is just the number 1. And likewise, the position operator acting on state 2 is 2 times state 2. Right? So here, state 2 is an eigenstate, and the number 2 is the eigenvalue. Okay? And this makes sense if we look at the matrix, right? If we have this matrix, x hat is 1, 0, 0, 2. If you just calculate the eigenvalues of this matrix, That's what they are, 1 and 2. Okay, so if you calculate it using whatever you learned about eigenvalues in a linear algebra course, right? You get these numbers, 1 and 2. Okay, and the or if you type it into your favorite software, Mathematica or whatever else, right? And you know, click on calculate eigenvalues, right? You get the numbers 1 and 2, right? So that's another way of saying that this matrix has all the information that there is about the position operator, right? That it knows the eigenvalues, the eigenvalues are 1 and 2, and the eigenvectors are 1, 0, and 0, 1, like that. And this 1, 0, this is equivalent to writing the state 1. And this 0, 1 is equivalent to writing the state, the ket, 2. Okay. If that's not clear, that's because 1, 0 means 1 times ket 1 plus 0 times ket 2. So it's ket 1. Okay. And likewise, 0, 1 is 0 times ket 1 plus 1 times ket 2. So it's ket 2. Okay, so that's the position operator, okay? And you know that one thing you can do with a position operator is to calculate expectation values, okay? So that's something we've been doing all semester, right? If you want to know the expectation value of the position in the wave function approach, that's this average position, that's the integral of psi star of x and t times x times psi of x and t dx. Okay. Now, what if we want to do that in the matrix approach? So the expectation value of the position, that, excuse me, and back on this wave function side, right, I should say this could be written as the inner product of psi x psi, like that, right? So on the matrix approach, it's the same kind of story. The expectation value of position is this inner product of psi x psi. But now what that means is the psi on the right, the ket, is psi 1 of t, psi 2 of t. The operator x is the matrix that we figured out, 1, 0, 0, 2. And then the bra psi is psi 1 conjugate of t, and then psi 2 conjugate of t. And, you know, we can multiply this out, okay, following the rules of matrix multiplication. And to multiply this out, well, let's do it step by step. Okay, so first I'm going to combine the matrix with the ket over there. Okay, so I'll just recopy the bra. Psi 2 star of t. Okay, I recopy that. And then this matrix times the column vector on the top, that is multiply across and down, okay? So it's 1 times psi 1 of t and 2 times psi 2 of t, okay? And now if I multiply this, I can combine the first times the first plus the second times the second. So that makes psi 1 of t magnitude squared plus 2 times psi 2 of t magnitude squared. And yeah, this is right? This is how you would get the expectation value of x, right? Because it's 1 times the probability that the electron is in position 1 plus 2 times the probability that the electron is in position 2. And that's the way you calculate expectation values or averages in probability theory. Now, it also works for operators squared, right? And so, in the wave function approach, we've talked about the operator x squared, right? So it's the operator that says whatever function you have, multiply it by x and then multiply it by x again. Okay, you do it 2 times. Okay, that corresponds in the matrix side, the operator x squared is a product of 2 matrices. It's the matrix for x times the matrix for x. Okay. So if we multiply these matrices with the rules of matrix multiplication, what do we get? Right? Well, it is here, first times first plus second times second. Okay, so 1 times 1 plus 0 times 0. That's 1. Okay, then for the upper right corner, it's 1 times 0 plus 0 times 2. That's a 0. Then for the lower left corner, it is 0 times 1 plus 2 times 0. That's a 0. And then for the lower right corner, it is 0 times 0 plus 2 times 2. That is 4. Okay, there's the x squared operator. Okay, and so if I wanted the average of x squared, the average of x squared, just keep repeating the same thing sort of mechanically. Say psi 1 of t, psi 2 of t star row vector, then the matrix 1, 0, 0, 4, and then the column vector psi 1 of t, psi 2 of t. Okay, and so this is, I'll skip some steps and just multiply this out. It's psi 1 of t magnitude squared, plus 4 times psi 2 of t magnitude squared. Okay, so this is 1 squared times the probability that the electron is at 1 plus 2 squared times the probability that the electron is at 2. So it works, right? And so this kind of approach is well suited for doing stuff on computers because you're just working with tables of numbers. So that corresponds to what you've grown to know and love, or at least know, for working with expectation values for wave functions. So then, there's uncertainties. Right? You could talk about the uncertainty of x is the average of x squared minus the average x quantity squared. And that would work over here too. The average of x quantity squared. Okay. How are we doing with this? Does this seem reasonable? Okay. I'm not done yet. Huh. I can keep going because there's more stuff that we've done with quantum mechanics that we can still translate. For example, how about Schrodinger's equation? Okay, let's do Schrodinger's equation. Okay, so we have IH bar, the derivative with respect to time of this wave function, x and t, that is equal to the Hamiltonian operator acting on the psi function of x and t, right? That is what we have for Schrodinger's equation in the wave function approach, right? And this is where the Hamiltonian is negative h bar squared over 2m second derivative with respect to x plus v of x. Okay, so this is Schrodinger's equation on the wave function side. Okay. What about on the matrix side? Okay, we want to say an analogous thing for Schrodinger's equation. So that means we need to say that IH bar times the time derivative of the state, whatever is the state, written as a ket like that, has to be equal to the Hamiltonian operator acting on this state, this ket. Or because the ket corresponds to a column vector, I could write Schrodinger's equation that way. Right? So I could say I h bar and the time derivative of the column vector psi 1 of t, psi 2 of t is the Hamiltonian operator acting on psi 1 of t, psi 2 of t, like that. Okay. Now the column vector, the derivative of a column vector is the same as the column vector of derivatives. Okay, so this is equal to a column vector, which is I h bar d psi 1 dt and I h bar d psi 2 dt. This is equal to the Hamiltonian operator acting on psi 1 of t, psi 2 of t. Okay. Now here I say the Hamiltonian operator, but we know that operators are represented by matrices here. So the Hamiltonian operator must be some matrix. H11, H12, H21, H22. Okay, and then this is a matrix equation. Okay, so this is an equation for how the functions psi1 and psi2 evolve in time. Okay, and the time evolution is coupled. Okay, so if we do this matrix multiplication on the right, this says that I h bar d psi 1 dt, I h bar d psi 2 dt, that's equal to h11 psi 1 plus h12 psi 2 and h21 psi 1 plus h22 psi 2. Okay. So this then is a pair of differential equations. It says IH bar, these things should really be written as ordinary derivatives, not partial derivatives, because these things are only functions of t, not functions of position. Let me change that to ordinary derivatives. Okay, so d psi 1 dt is h11 psi 1 plus h12 psi 2. And IH bar d psi 2 dt, there's no dt, is h21 psi 1 plus h22 psi 2. Okay, so the Schrodinger equation in this wave function approach is a partial differential equation. And here it is a set of coupled ordinary differential equations. So if you wanted to solve this, well, somebody would have to tell you what is the Hamiltonian matrix, right? So what are these coefficients? What is the Hamiltonian matrix right here? And then if somebody tells you that information, then this would be a set of coupled ordinary differential equations to solve. In the next class on Monday, I will solve something like that, okay? So I will just make up an example for the Hamiltonian matrix and show you how to solve the differential equations and show you how that is analogous to the solution in the wave function approach. But for now, I better stop. Okay, so let's stop here for today. And then what? We'll stop here for today, and then let's take a 15-minute break or so. And then at 2 o'clock, I will post the test, and you guys will email it to me by 2 o'clock p.m. tomorrow. And I just want to emphasize, I really don't expect you to spend 24 hours working on this thing, okay? I really expect this will be like a 1 or 2 hour job, okay? But yeah, you can have 24 hours, and so, you know, you can have extra time. It should be extra time, I think, and I hope you won't be limited by time. Okay. So let's stop here. Good luck, everyone, with the test, and I'll look forward to getting your emails by 2 p.m. tomorrow. All right, thanks.